Hello, everyone. Welcome to my talk. My name is Kak Hoàng Ngô. I'm working in Chalmers University of Technology, and I'm going to present to you a work on the optimal degrees of freedom for the non-coherent MIMO channel with generic block fading. And this is a joint work with Sheng Yang from Soft-Transibelec, France, and Maxime Yu from Huawei Technologies, France. So this is the outline of my talk. First, I will give some background on coherent and non-coherent communications. Then I will present our main result, which is the optimal degrees of freedom for the non-coherent MIMO channel. After that, I will show the converse proof, and then I will conclude the talk. So let's start with the coherent MIMO communication system. So we consider here a MIMO channel with N transmit antennas and N receive antennas. Channel output is given in this way. So it is for the product of the channel and the transmitted signal plus the noise. Here we assume that the channel matrix is the full rank almost-surely. We consider an average power constraint, and we assume that the noise is Gaussian distributed. Then it has been shown that the capacity of this channel scales at the minimum number of transmit and receive antennas multiplied by the log of the SNR and plus a constant term. So here, this number, which is the minimum number of transmit and receive antennas, is the pre-log of the capacity with respect to the SNR, and it is called the degrees of freedom of the channel. This result is awesome because it says that we can actually scale up the capacity just by adding more and more antennas. However, this result it relies on an important assumption, which is the channel matrix should be known a priori to the receiver. But in practice, the channel matrix varies over time and it is not given for free. We have to estimate it and then use it to communicate coherently, or we have to communicate without the knowledge of the channel matrix. So if we assume that the channel state information is not known a priori, then we have non-coherent MIMO communication. And here again, we consider an M by N MIMO channel. Now we assume that the channel matrix is constant during each duration of T symbols, and T is called the coherence time. But it is unknown a priori. Then we can actually stack the signals and the noise within a coherence block to get this output signal. And again, we consider an average power constraint. Now, if the coherence time is 1, that is the channel changes every symbol, and then we have a fast fading, and it was shown that the capacity of this fast fading channel scales at the double logarithm of the SNR plus a constant, which is called the fading number, and a vanishing term. So actually in this case, the optimal degrees of freedom of the channel is 0. And the main assumption here regarding the channel is that the channel matrix has a finite entropy and finite second moment. And this is referred to as a generic fading setting. Now, if the coherence time is larger than 1, then we have block fading, and the capacity is shown to have this form. So it is this number, which is m star times 1 minus m star over t, and where m star is given here, which is the minimum of the transmit antennas, number of receive antennas, and a half of the coherence time. And this is multiplied with the log of the SNR plus the constant term and plus vanishing terms. So here the optimal degrees of freedom is actually this number. And to establish this result, the assumption is stronger. They assume that the channel is the IID Rayleigh fading. The channel matrix follows a Gaussian distribution. Now let's take a closer look at the optimal degrees of freedom, which is given here. There are some insights that we can infer from this result. First of all, we can achieve this optimal degrees of freedom by using a simple pilot-based scheme. So basically, we use the M-star transmit antennas. We transmit the pilot sequence in the first M-star time slots of the coherence block, and we transmit data in the T-1, T- the M-star remaining time slots, and we can achieve these degrees of freedom. Secondly, as I mentioned, we should use only M-star transmit antennas instead of M antennas. And actually, if we insist on using more antennas than M-star, then we can actually reduce the capacity. We can directly see that in this figure. So here, the degrees of freedom is plotted versus the number of transmit antennas for the non-coherent case and the coherent case. We see that if we increase the number of transmit antennas to be larger than the number of receive antennas, that actually the non-coherent degrees of freedom is decreased. This is in contrast with the coherent case, where the degrees of freedom is always increasing, or at least stays the same. Well, the reason for this behavior is that when we keep increasing the number of transmit antennas, at some point, we don't increase the spatial dimension anymore, but we add more and more channel uncertainty to the problem. Well, so these insights are awesome, but we can ask ourselves, is the assumption of the IID Rayleigh fading really necessary to establish this optimal DoF? Well, the answer, or our answer, is no. This optimal DoF actually holds for the generic fading in general, and this is the main result of our paper. So now if you decide to leave, this is the message that I would like you to take away. And if you would like to see how we establish this result, I invite you to stay and I will show you why. So again, the optimal degrees of freedom can be achieved by a simple pilot-based schemes. Now we focus on the converse proof. And for simplicity, we consider first the MISO case where the transmitter has M antennas and the receiver has only one antenna. We consider an average power constraint. We assume that the channel is in generic fading in the sense that it has finite entropy and finite second moment. Now, for this case, the optimal degrees of freedom is given by 1 minus 1 over the coherence time. And we are going to show why it is optimal. To do that, first, we write the mutual formation between the input and the output as the difference between the entropy of the output and the conditional entropy of the output given the input. And the conditional entropy can be shown to have this form. Now, the main difficulty is to bound the entropy of the output. And to that end, we apply the duality approach. So the entropy of the output can be written as the mean of the minus log of the BDF of the output. So here the BDF P is actually the true BDF of the output, which is imposed by the signal, the noise, and the channel. And we can show that actually if we replace this BDF by an arbitrary BDF Q of the vector Y, then we obtain an upper bound on the entropy of the output. And the key here is to choose a proper auxiliary distribution Q so that this upper bound is tight. To do that, we first decompose the output vector as the product of a scalar sigma and a unit norm vector V. The Jacobian of this decomposition is given as a function of the scalar sigma here. And we choose the auxiliary distribution of Y as follows. So first, we let the unit non-vector V to be uniformly distributed in this stiff field manifold, which is basically the space of unit non-vectors. And we let this vector to be independent of the scalar sigma. Now for sigma, we choose is the BDF as follows. So we let the auxiliary BDF to be proportional to the ratio between the Jacobian and a term which is 1 plus the sigma square to the power alpha, where alpha is just the coherence time plus a small number. Now we can derive and can expand the mean of the minus log of the auxiliary BDF in terms of the mean of the minus log of the BDF of sigma and V and the Jacobian. And by blocking these expressions, we see that we get a simple form of alpha multiplied with the mean of the log of 1 plus sigma square. So first we can fraction this alpha into alpha minus 1 and 1. And for the first term, we use the Jensen inequality to pass the expectation inside the log to have the mean of sigma square inside. And finally, sigma square is basically the power of the vector of the output vector y. So by putting back the y here, we have this expression. So basically, we have to up about the two terms in blue here. And after some manipulations, we can see that the first term can be up bounded by the log of the SNR plus some constant term. The second term, where the expectation is outside of the log, can be up bounded by this expression. And you should recognize this because this is also the expression of the conditional entropy of the output given the input. So they cancel out. And by introducing all the bounds into the mutual information, we can have this upper bound of the normalized mutual information between the input and the output, and the normalized pre-log is given by alpha minus 1 over t. And recall that alpha is basically just t plus a small number. We can take this small number to be arbitrarily close to 0, and then the optimal pre-log converges to t minus 1 over t, which is basically the optimal degrees of freedom of the channel that we want to show. So this completes the proof for the MISO case. Now for the MIMO case, the optimal degrees of freedom is given by this formula. And we are going to show why it is optimal. Again, we write the mutual information of the input and the output as the difference between the entropy of the output and the conditional entropy of the output given the input. And again, this conditional entropy can be expressed in this form. We use, and again, to up about this entropy of the output, we apply the duality approach, and we use this auxiliary output distribution Q. Now, the main difference with the MISO case is the choice of the auxiliary output distribution Q. And we choose it as follows. First, we decompose the output matrix Y using the single value decomposition. So Y is the product of a unitary matrix with a diagonal matrix that contains all the singular values of Y and the omission of another unitary matrix. The Jacobian of this decomposition is given by this term, which is upper bounded by a function of the singular values of Y. Now we choose the auxiliary distributions as follows. So we first let the three matrices to be mutually independent. And then we let the matrix U to be uniformly distributed in the Stafford manifold we let the matrix V to be uniformly distributed in a submanifold of this state field manifold. And finally, for the singular values, we choose their joint auxiliary BDF to be proportional to the ratio of the upper bound on the Jacobian and a term which is the product of the 1 plus the square of the singular values of the matrix Y. And we have the power alpha I here, where alpha I is given by this formula. And then using this auxiliary distribution, we follow the similar manipulations as for the MISO case, and we obtained this optimal DOF. So in conclusion, in this paper, we have proved that the optimal degrees of freedom for the non-coherent M by N MIMO channel with generic block fading having coherence time t is given by this function, by this number, which is a function m star and the coherence time t, where m star is given by the minimum of the number of transmit and receive antennas and 1/2 of the coherence time. And to achieve this optimal degrees of freedom, we can use a simple bilock-based scheme. And the main technical contribution of our work is the converse proof, in which we adopt the duality approach, and we choose an auxiliary output distribution based on the singular value decomposition of the output matrix. So that concludes my talk. If you have any question, please give me in the Q&A, or you can also send me an email. And thank you for your attention.